some people were interested in the idea this might be some sort of classroom environment. And while we're not actually teaching this as a class per se, there's this great wiki site called Wikiversity, whose job is to put together stuff that might be classroom stuff. So we've got something off of one of the Linux area pages in there that's specific to this whole kernel study idea we're throwing together, and therefore the batch of us here at SVLUG, while we're studying kernel stuff and yakking about it and asking questions and stuff, can contribute to this project. Jim put a bunch of material into the page for this last session, and he encourages a bunch of the people here, or even who aren't here right now but like sort of had the interest and couldn't make it, to log into the wiki page and add questions and add answers and add, I don't really know if this is the right thing or the wrong thing, or it used to be different but now it's this kind of comments, so that the information grows, because there's hundreds of us in SVLUG and only dozens of us showed up, and we all know stuff that's different stuff, so it can help. The Wikiversity is at en.wikiversity.org, or at least in my case it is, because I only read English.
And do a search on reading the Linux kernel sources. Yes. Yes, or if you're at Wikiversity and you type search and then just Linux, it brings you to the main Linux topic. And currently there's only a few items down towards the bottom of that page, of which one of them is mine. Or ours, I should say.
Here under the search for Linux, the content to study includes the Linux 0.01 tar, types of GUI, directories in Linux, basic comments in Linux, and the big one I was talking about a minute ago, reading the Linux kernel sources.
All right, repeat this. What's the URL for lxr.whatever?
Okay, the question is, where is this kernel reference site that we were using last week? And the URL for it is
what's that fabulous website?
Right, lxr.linux.no. The .no is actually in Norway, for those of you unfamiliar with the two-letter country codes. And LXR is Linux Cross Reference, the X meaning cross. So, and on that note, I'm actually going to bring that site up. lxr.linux.no. It'd be really embarrassing if I got this wrong now.
So, Jim, what is Iceweasel?
Iceweasel is Firefox under a different name. And the reason for that is that Firefox is trademarked. And so the company, which I guess is a non-profit organization or a not-for-profit organization, but the company behind Firefox, which is the Mozilla Foundation, they trademark Firefox, and if you want to modify it in any way, including patching it, then you cannot distribute it under the name Firefox. It's open source, but they don't want you going around and fiddling. People are making gestures at me while I'm answering a question. Anyway, they don't want you fiddling with the code underneath it and still calling it or distributing it as Firefox. So various distributions have renamed it in various ways, like Debian currently calls it Iceweasel. And what was the name that Red Hat came up with it for it in the recent Red Hat Enterprise Linux releases? Anybody remember? Anyway, you'll find various different names up there, but it's really just Firefox.
I have a silly question.
Okay, I'm listening.
What are the typical values for a Jiffy? How long should a Jiffy be?
Okay. The question was, what are typical values for a Jiffy? Actually, the better question, and this is actually one of the FAQ questions if you search online, what's a Jiffy? And specifically, in very early versions of the kernel, they came up with this concept. There are some times where you want to use a delay loop, a busy delay, where you're just going to do a no-op, no operation on the processor for a certain number of times. This is for very short delays where the overhead of programming one of the system timers and waiting for it to trigger and the amount of jitter inherent in that process would be too long. So when you need, for certain types of device drivers, you need very short delays, then what they do is they program the timer to trigger at a certain amount of time, programmable interrupt control timer rather, and then while the system is doing absolutely nothing else during kernel boot up, it actually calculates the number of times that it can do nothing before that interrupt triggers. Those are Jiffies. And the number of those, the calculation of how many of those they did, is referred to as BOGO MIPS. So very early in the kernel boot up, when you see calculating blah, 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 n number of BOGO MIPS, that's why they were doing it and what they were doing. There's actually a FAQ on that topic somewhere online. So Warren, since I'm on your machine, why is your mouse not working for me?
Warren's not in the room.
Dude!
I would like to point out that we have a small display over on the right-hand side which allows you to see things that we can write. And we've written the URL for the Linux sources, lxr.linux.no.
Okay, so if a volunteer wants to go also right over there, wikiversity.org. Up there on the top. All right, so unfortunately, this system has decided to not talk to me anymore.
Is it a USB mouse?
Well, it's just a glide point on it, but nope. Alt-Tab isn't working. All right, so that's all right. We'll do without for that for a moment. Let's go into a little bit of review of what we covered last week. So, does anybody remember what we covered last week? How many people were here last week? Returning people. Most of us. Good. All right, and how many people actually did anything that you would call homework? A little bit. I noticed that basically nobody edited the wiki, which would have been nice. Yeah, just a minute ago. Nobody edited it as of last night. So what was the main topic from last week?
Steps before the init process is started.
Well, okay, so one of the main themes was, where do you start reading the Linux kernel sources? Right, you got 1.5 million to 2 million lines of code, and the very concept of where do you start reading is actually kind of slippery. I mean, the most obvious place where you would start reading any normal C program is you'd look for main. You know, int, main, blah, blah, blah. And there really isn't such a thing for the Linux kernel. So we discussed, well, from a CPU's point of view, where does a CPU start reading the kernel source code? You've got some kind of bootloader, a Lilo, Grub, whatever. It's loaded this thing into memory, right? We know on a PC, that's a compressed kernel image, mostly for historical and weird memory management reasons. So the very header of this has to decompress it, and there's a little bit before then. So last week we looked at bootsect.s, capital S, which at one time you could DD a kernel straight to a floppy and boot it right off of there. Now, as we read in about 2003, they ripped that out of there, so now it just gives you a, what was the phrase they used? A bugger off was the label of the function. So they don't support that anymore. And then I had found, and I had remembered somewhere in there, I had not remembered where, but years ago, the last time I was trying to read the kernel sources, I had found the place where they set up the kernel process, excuse me, the CPU into protected mode. That transition is a little ugly, right? On an x86, remember we talked about real mode and protected mode. So in real mode, you have a segment offset architecture, which means that your segment is any of every 16 bytes, there is a segment location. And from that segment, you can go up to 64K. All right? So when I used to actually teach people back when I was worked for companies like Quarterdeck doing tech support, I used to also train some of their tech support people. And the analogy I used, coming from my days as an electrician, is if I'm standing next to this wall, I can reach to, let's call it 6'6", all right, or 6'4", all right, so think of 64 inches. Now if I stand a ladder up next to that wall, and I step up 16 inches, now I can reach from my feet up to 6'4" above where I'm standing. So if I climb to the top rung of the ladder, well, if I try to do that, I'm going to bump into the ceiling before long. So on the original 8086 processor, that was the problem. That as you got high enough segments, then you couldn't reach the full 64K because that was the end of the address space that was supported on the processor, so you were hitting the ceiling. When they went to the 286, it was sort of like having the ceiling in the same place, but instead of a hard ceiling, you got these tiles here, right? And those tiles you can think of as something called the A20 address line. Starting from 0, A19 was the 20th address line on the 8086. That could get you up to 1 meg of address space. 640K plus the people who actually designed a PC around this processor reserved a bunch of space at the top, 384K of address space they reserved for adapter cards, ROMs, and other non-RAM. The A20 is the first address line past A19, and in the number of years that IBM had been shipping PCs with a 20-bit address bus, up to A19, they actually had written some software that was designed to hit that and wrap around and keep going. So they actually needed to route the A20 address line, of all places, through their keyboard so that it would emulate this behavior so their software wouldn't break when they suddenly extended to a new architecture. Yes, Heather?
Well, I'm not sure if I'm going to...
No, her name's Heather.
I'm not sure if I'm going to sound like a shill or a heckler here, but what does this real mode versus all this exciting protected mode address space have to do with Linux?
Because the processor still starts up in real mode, so we still have to get to protected mode before we go there. And when this thing here is responding again, we can actually go to the piece of source code that actually does that. But first, or until that happens, I was going to at least describe what is a global descriptor table, and what's a descriptor, and what's a selector. That's why I'm getting there. How many people want to understand a little bit about how the processor goes before trying to read any of this assembly source code? Okay, so I'm not totally off base here.
There's a decent number of hands in the audience, in case anyone was curious.
Okay, so as I was saying, you've got this A20 line, which for backwards compatibility reasons is not enabled when the machine first boots up. So what they have to do is talk to a particular register, it turns out it's actually in the keyboard controller chip, to tell it to enable the A20 line. At that point, when you're in real mode, you can now address almost 64K, that's 64K minus 16 bytes, above the old ceiling, because you can stand on the last rung of the ladder, 16 bytes below the end of the address space. So those of you who remember the bad old days of DOS and DOS memory managers might remember hearing about HighMem and using the HighMem.sys or using QEMM. What those were doing is enabling the A20 line and then managing the access to that little chunk of address space, which on a 386, and that was, skip the 286, it was useless. For anything beyond running something like OS2 or running DOS a little faster, the 286 did not have the memory management features to do anything really useful because it couldn't remap the memory around. There's no virtual memory management. You did have the HighMem.sys, you could create a little RAM disk up there, you could do little things, you could have extended memory, or you could go into protected mode, but the protected mode on the 286 only supported a different form of segmentation, the selector concept. It didn't support virtual memory. That didn't come out until the 386. And that's one of the reasons why Linux can't run on anything less than a 386, except for that weird ELKs that somebody asked about last week. Yes, John.
Add a little thing. I think you made. So in one of our first presentations, we talked about how Linux ran on a variety of platforms. This was not true in the beginning. So part of the reason why we're talking about all of this x86 is because that's the first platform that Linux ran on. And in some sense, it's the best platform it runs on.
That's one reason. The other reason is simply because that's the kind of processor that all of us have in front of us. I mean, these days you buy a machine from Apple, what kind of processor is in it?
I'm not disagreeing, but what I want to point out is Linux began as a spin-off of Minix, okay, which is an operating system that was originally a teaching operating system that was supposed to exist only on PCs because that's what people could afford, okay? And so the Minix kernel, I mean, there's a T-shirt you can go around which talks about when Linus says, you know, I'm creating this new operating system in comp.sys.minix. And
famous Flame Wars 101.
okay, and so when you're talking about how Linux starts up, it started up from the very beginning of being a x86 kind of stuff that Minix was on, going through the 286, going through the 386, and so some part of the Linux startup sequence is actually a legacy of its own history. So that's the thing that we're trying to tell you, is that this history, although it seems arcane, is actually useful.
Meanwhile, I'm going to take the bull by the horns over here, so to speak, and reboot this with extreme prejudice. Well, no, it was beyond three-finger salute. Yeah, I imagine he does not have Magic Sysrec enabled on that machine, so it was hold the power switch down for a bit. Well, life's hard.
Not really so much for the mic, but if anybody wants something to go into the wiki page and you just don't have a laptop in front of you, feel free to sneak up behind me. I can type fast.
So I was also going to mention the difference between paging and swapping.
Not yet.
Not yet?
John was saying he was going to mention the difference between paging and swapping, and among other things, that difference really doesn't exist in Linux because Linux does not actually support true old-fashioned swapping.
But the older versions did.
Sort of. But also it's kind of meaningless until you actually are doing the memory management, which we hadn't gotten to yet. All right, so while that's booting, so you've got the real mode, you got your A20 address line enabled. Now, before you can actually access memory beyond a little past 1 meg of address space, the next thing you have to do is shift the machine into what's called protected mode. Now in protected mode, what happens is the registers that used to be segment registers now become what are called selectors. They select a particular entry in a thing called a descriptor table. And there are several different types of descriptor tables. So what happens is each of these entries describes a region of memory that you're allowed to use. And that's where the protection model comes in. Because I have a descriptor table entry that says my code segment starts here and extends this long. My stack segment starts at this other space and extends this long and grows downward, all right? And so on for each of your different registers. So in order to shift into protected mode, you have to set up this descriptor table. The one you have to set up yourself, for yourself, is the global descriptor table. There's also a local descriptor table, and you also have to set up an interrupt descriptor table. Now, the interrupt descriptor table has to consist, absolutely must consist of 256 entries, one for every one of your interrupts. For those of you who are curious, Intel has this bizarre nomenclature by comparison to the rest of the world. They have an instruction named int, INT, which is only kind of loosely related to the concept of an interrupt request, an IRQ, which is a hardware event that triggers some sort of activity in some in some chips besides the processor, and then can trigger some events in the processor. The reason I say that they're only loosely related is that there are 256 interrupt vectors. In real mode, that's the first 4K of address space. of memory is the vector table. And then in the interrupt descriptor table, each one of the entries in there is pointing at something. Now they use these not only for hardware interrupt request servicing, but also for certain types of software events, including things like, how many people here have ever heard the phrase exception 13 from your old Windows days? Later they renamed it to general protection fault. The reason it's called exception 13 is because when you're in protected mode and you attempt to address any memory, any of your instructions attempts to access memory that is outside your descriptor selector, that becomes an illegal memory access, and that raises a processor's own internal exception handling, which is vectored on 13. So in other words, they use these. Some of them are for hardware interrupts. Some of them are for processor exceptions, such as divide by zero, single step, illegal memory access, things like that. I have no idea who's calling me. Huh. No, roommate. She's probably asking if we're going to LA this weekend, which we are. And then the rest of these interrupts are actually used as basically as a programmable library of single instruction function calls. So, for instance, all of the system calls in Linux are vectored through int0x80. So in other words, by tradition, the top half of the interrupt vector table, or of the available interrupts, was used for kind of user interrupt vectors. And so what Linux did is it used int80 for all of its system calls. For those of you who remember the old DOS programming days, how many people here remember 21 hex? int21. Exactly. int21 was used by DOS for its dispatch of almost all of the DOS services. Another one is int10, which is your old BIOS interrupt for video services. Why am I mentioning that? Because if you're reading the boot code in Linux, you're going to find a bunch of references in video.s, for example, where they're fiddling with int10 before they've shifted into protected mode, before the kernel's own device drivers are in place. They're having to call some of these BIOS level functions to even get there. Another one, let me see if I can remember it. The disk drive vectors. Anybody remember that one? I should know that one. I don't remember it off the top of my head.
Google for Ralph Brown.
Ralph Brown's interrupts table.
Actually, there are very nice Wikipedia articles on both the phrase extended memory and interrupt.
I'm glad. Because I'm probably getting some of the details wrong. It's been so long since I've ever actually had to do anything with them. Incidentally, Ralph Brown's interrupts list is listed in the comments of some of these .s files as the source of their information. Wow, I remembered my new password.
High five.
Yay. Can I change a password and remember it and talk all at the same time?
Don't worry, I've sent for Warren.
Why?
Is it
So he
working
can
now?
help you out.
Well,
Heather, is it now working?
Good question.
it's going to work now. It may hang again. I don't know why it hung in the first place. It didn't like us. Maybe it was the Ice Weasel Flash player that keeps kicking Heather's machine out of X.
That's what I get for using 64-bit systems.
Okay, now.
Video.
Bang. X term. You lie. Like a dog. B-FN.
Do you think we should mention top hat and bottom hat?
No, we're nowhere near there.
Oh, okay. Just trying.
What? Oh, yeah, it helps if you
Anybody else, while
actually type a
looking
color
around
in
for
there.
stuff related to this kind of thing, find any other really cool URLs about kernel stuff?
great lead.
Well, I'm asking this because I'm typing them into the page.
There's one at www.tamacom, TAMACOM.com.
www.tamacom, T-A-M-C-O-M.com.
Actually, the one thing that we could use Warren for,
.com?
most importantly, would be to bring the wireless back up.
What? The wireless is fine.
I mean on his
Oh, on
laptop, because I don't have root access to his machine. All right.
T-A-M-A-C-O-M?
Yeah,
Okay.
What's this URL?
tamacom.com. It's
Okay.
another annotated Linux source online thing.
All right. Well, if Warren isn't back in a minute, then what we're going to do is go up to maybe Plan C on the laptops on the screen here. I hope that won't take too long. All right. So back to what I was talking about. So I cannot give a full description of the x86 processor's global descriptor table and all that stuff, frankly, because I get confused when we get down a little deeper than that, and I don't remember the ugly details.
There may be a Wikipedia entry.
There are actually excellent online resources, and you can actually figure out some of this. Remember last week I showed us head.s, capital S, and there was startup_32, which is, as far as I can tell, the first instructions that the processor executes in the Linux kernel after it's shifted into 32-bit mode. The process of shifting into 32-bit mode is embedded in a file named setup.s. And that actually contains various includes that describe the global descriptor table and interrupt descriptor table setup. It has an interesting comment in there, something about there being 32 tasks that it's setting up. In other words, the global descriptor table, you statically set up, you initialize it with a certain number of entries, and there's a comment in the source code. Thank you. So Warren, for reasons unknown, the mouse locked up, so we hard booted it. And I will only express the minor concern that it may do that again. Let's go back one. Okay, so I'm just fumbling around here remembering where this stuff was in Arch, that's architecture, 386 boot. Here's the setup.s. It also includes video.s near the end of it, which sets your video mode before you go into this. I'm going to enlarge the text here so you can see it better on the screen. That looks big enough. I'm also going to move this window over so you can all see it. We good to go there?
Yeah, you can
Yay.
to the right if you'd like.
GT. Okay. So here's a part where it's setting up the descriptor tables. And somewhere in here, there's also some weird stuff like this end if Voyager. If I recall correctly, Voyager might have been an SGI workstation machine, which used an x86 processor, but was otherwise not at all like a PC. So it's kind of a weird beast. You're going to see interesting things like that scattered out through the kernel. How many people know what this means? XOR AXAX.
Clear.
Right. So why aren't they using move AX0?
Speed.
Because this is faster. And why aren't they using sub AXAX?
Because it sets the carry bit.
Because it would fiddle with your bits. Exactly. You want to clear a register and not fiddle with your bits, you want to do it right darn now. XOR register to the register. That makes me sound like I know so much about assembly, doesn't it? Ha ha ha.
It's disturbing, actually.
Considering how little I actually know about assembly, yes, it is disturbing. But we'll
I know somebody with that as their nickname.
Okay, so here's the line where they're talking about how they're going to jump to startup 32. But before we can do that, yeah, I was going to say something about that. This is one of the scariest comments I have seen anywhere in this. And if you read it, you can see what it's doing. Right? It's doing a short jump to there if the A20 line isn't enabled. Now, is it just me, or does this make you feel compelled to maybe put in a little patch, maybe grab a couple of those lines from sod off or bugger off, you know, in the other file and say, why don't we give the guy an error message at this point, guys? You know, if the A20 line doesn't work, maybe we could like decide to try it 200 times and then give up or something. Why just sit there just looping on ourselves? I don't know. I wonder if Linus would accept a patch from me on that. Or if he would just laugh at me and say, dude, it's been like that for 10 years and it's never been reported as a problem.
So where is the,
Shouldn't it be a problem, though?
where is the label 1B? I'm noticing.
It's a label 1, and the B is a modifier to say that basically a jump if equal, that's jump if the 0 flag is clear. Because the previous arithmetic instruction, the compare long, actually sets flags, which is actually all it does. And there are various variations of the jump instruction which can have different forms depending on the length of the argument. Because we're doing a short jump, they're adding the B to the end of it. This is a funny form, and right up at the top, remember this line number for me for a second. Right up here at the top, I believe there's a little thing here that says, basically in the little credits file here, somebody talks about how they converted it from the AS86 notation. They ported it into whatever assembly language notation this is, which is a different assembler. So the assemblers that you're used to reading might use different, like they might not use dollar signs or percent signs for the percent signs for register names, dollar signs to dereference. In other words, various different assemblers are not standardized to one another, even on the same processor. So there are some assemblers where when you're saying, I want to use the contents of this register as a pointer to an address, and that's what I want you to modify, you put square brackets around the register name. In others, like this one, I think you use a dollar sign in front of the register name. So dollar sign, percent sign AX says, take the contents of the AX register, use it as an address, and do this to what that address is currently pointing at. So you're going to find that some of the instructions have, different little suffixes on them for move long or move word or move short. And some of the other things are going to have things that say that they're a byte value or a word value and how they're aligned. So this stuff is a lot harder to read, especially since I don't actually know. Okay, so somewhere in there is transcribed from Intel AS86 by Chris back in 1999. That's why it might look a little different than earlier versions that you saw, and it might look a little different than any assembly language programming you've ever done in your favorite assembler, whatever that was.
Okay, although this is unlikely, I thought I would mention this part. The Intel instruction set allows you to have different displacement fields in a jump instruction. Okay, so you can have a short jump, you can have a long jump, you can have what's called a huge jump. Okay, and so they have adopted since Intel owns the AS architecture, most people would assume that this is going to be encoded in the instruction field, but it's actually encoded in the displacement field in gas, which is an unusual convention.
Yeah, that's actually called the operand, the thing that's after the operator or the instruction. Okay, so one of the reasons why last week we talked about possible ways to read the source code by going in where the CPU goes, but one of the things that we said at the time is, well, gosh darn, that's kind of hard because now you have to jump right into assembly language rather than reading any C, which is a whole heck of a lot harder than reading the C. But we're going to do a little bit of it anyway because we're clever and we can figure things out. So we saw that scary little thing down here, but the other thing I was looking for was, I'm going to search on GDT again. DT. Compute the base. So you see funny things like this. And I frankly do not understand where they're talking about, wait a second. They've got a startup 32 label here, and then they've got that jump to startup 32 in head.s, and I don't see how they're linking the two of them. So that's a little confusing to me. If somebody can explain it, I'd love to hear it.
I believe that they use a linker script to do that, don't they?
Maybe. That's what one of those LDS scripts is for.
I think so. I think that that's where the 16-bit startup code is.
Well, this should actually be 16-bit here,
You're right.
Well,
because we haven't gone into protected mode.
except startup 32.
Startup 32, though. I'm not sure.
Yeah, I'm saying this label, but the comment says the actual label we're jumping to corresponds to the one that's in head.s, even though there's a label of the same name right here in this file just below us. So,
Well, I noticed that, for example, it says .code32 and .code16, and those are usually compiler directives to tell you, or assembler directives,
Right.
to tell you what you have, what mode you're in.
mm-hmm.
And so it looks like startup 32 is in .code32, which means that it's actually 32-bit code. And that's because
Well, by this time in this code, we have shifted to protected mode, so that makes sense. I'm just trying to reconcile the fact that we've got this label here, we've got an identical label in a different file, we've got two different things that I'm not sure. I mean, I'm sure that they eventually get to the other one from here. And maybe all the comment is saying is that this one here, after the end of this little block of code, ends up at this jump here, it's going to the other one. Because it's calculating what that address is going to be, and somewhere else, as he says in the linker script, is guaranteeing that the other piece of code is going to end up where this calculated it's going to be. So, pretty hard to read stuff. There was another thing I wanted to find in here where it's talking about the number of tasks that it sets up. So if you'll excuse me, I'm going to go, it's not in this file. Well, that explains it. I think based on that, if we go to one of these include files, now I notice for some reason, this thing isn't smart enough to see these includes and link me to it. So I have to go to it separately. And I think it was in segment.h. It's the other one where I was looking for this. So let me... It's actually one higher than that. It's in include. Now there's another thing. You notice that the actual include statement said include ASM/, but there isn't an ASM directory in here because when you install Linux kernel sources and you configure them, it creates a symlink down to the assembler that's appropriate to your system. So you're not seeing that on their website, but I just happen to know that you have to do that. And somewhere in here was segment.h, to where I think they talk about that structure. Layout of the per CPU GDT. So one of the things I was leading to here is I had never thought about it before I read this piece of code, but it's pretty obvious to me GDT has 32 entries. It's pretty obvious to me that a GDT, you have to have at least one GDT for every processor. I never thought about it before, but every processor on the system, when you go into multiprocessor mode, is obviously going to have its own stack. If nothing else, it's going to have its own stack. And since the stack selector is one of the entries in the GDT, everybody's going to have their own. So that implies that the way this thing is currently compiled, maximum number of CPUs is 32. Here, where they talk about per CPU and tasks, somewhere in there they say something about a task. What they're really saying is that I have one CPU, or one task per CPU in this table. Yes, you're looking stunned.
I'm wondering if I hit this. I have, for a client, I just did 16 DOM views.
No, that's all right, I'll just...
Oh. I'm just wondering, there's a client I'm working with that's doing Zen virtualization. And I set up a number of VMs to have 4 vCPUs each, and then had, a bunch of them. And so it was well over 32
how many
virtual CPUs on that one DOM 0 eventually.
CPUs are on the
I don't
machine?
know. That's what the whole point is. And I ended up crashing the thing out, and I'm wondering if that's what happened.
I doubt it.
I don't know.
Because
Anyway,
the,
that was it
the
seemed like it
Zen
might explain
DOM
it.
use, the user space DOMs, each of those is going to have its own GDT table.
But it still has to be mapped back and forth. So that's what I'm just, that's my whole,
But if the host hardware doesn't have more than 32 CPUs, I suspect what would happen is if you had a 64 CPU machine, like 32 real CPUs, each of which was dual core, if you had that, then the Linux kernel simply would not spawn tasks on those other CPUs. They would just sit there idle. I'm just suspecting this. Now, as an experiment, one thing we could do is it wouldn't be impossible to find a 4 CPU or 2 CPU dual core each system, set this to just 2, and boot it up and see what happens. I suspect you cat/proc CPU info, you'll find that you only have the 2 processors, even though it's a 4 CPU machine, and that other than that, I wouldn't expect you to have any other problems. But I'm totally guessing here. This is not an experiment I've run. Anybody here have a 4-processor system laying around? Not your laptop in front of you. I mean, just at work. Then you're just running a uniprocessor kernel. So you at least want to have a 4-processor system, run it with an SMP kernel, where you have manually patched this to GDT entries equals 2. Now you might want to actually do that at a higher level, and also in the make files say maximum CPUs is 2. So, because otherwise you probably will crash because there will be 2 different numbers there. This one and the one that you put in your make file. So anyway, back to the topic of reading kernel sources, we saw what I did. I got curious about some little detail in one thing, followed the link back, read another thing, and mostly I'm just reading the comments when it comes to this assembly language, because despite my knowledge of what XOR, a register against itself, does, I don't know assembly nearly well enough to trust what I'm reading without a whole lot of help from the comments. And if I had lots more time, I would spend more time reading, like, find the documentation for this particular assembler, whatever the heck it is, and go read what they actually mean in their notation. Get accustomed to that and do a little refresher on some of the other instructions.
Jim, there's a book by name Assembly Language Step by Step.
Yes.
Color book.
Old Abacus Publishing. I bought a copy for my father about 12 years ago.
Hold on a moment.
The comment was there's a book, assembly language step by step.
That has a whole section on this gas notation and how it's different from conventional Latin notation.
That must be a newer edition. He says there's the assembly language step by step has a whole section on the gas assembly language syntax. All right. So anyway, that got us a little further. Like I said, one of the things that I found a little shocking and a little scary, frankly, was this whole thing about, well, let's just loop here forever if the A20 line isn't set.
What is the A20 line, and does that loop get interrupted when the A20 line gets set?
Okay, I had described it a little earlier. I'll get to you in just a moment.
Newer source code, and it looks like they've changed that.
Really? Yeah? All right. What Paul is saying is he just was looking at some newer source code than what we've got here, and they've already fixed that or changed it to something else, right? Which I think is a little unusual. This was, I mean, what we were looking at was 2.6. What's up there at the top?
This is 2.6.24 that I'm looking at right now.
In this tree, it's
Okay.
22.
So,
Huh? Pardon?
22 in this tree.
Right, okay.
so and by .24 it's gone.
Okay.
In
Well-
2.6.23, I don't see the setup.s in the directory that you found.
Uh,
On 26.
You're,
In the,
I think that you guys might want to keep in mind that they moved around a bunch of the stuff for that combination of AMD 64
ah,
and
yes. Remember last week I mentioned that there was this movement afoot in around 2.6.24 where they're combining the x86 64 with the old 386 architecture. So this might actually have gone away as part of that effort. See? So I almost knew that and then forgot it.
It looked like the A20 had something to do with that Voyager code earlier also.
No, that was after the NDiff. A20, well, okay. On a Voyager system, the A20 line is probably not routed through the keyboard controller. Because, as I said, I think the Voyager was the SGI workstation. And that one, I talked to the people at SGI. I was actually teaching my Linux sysadmin class at SGI, and they told me a little bit about that thing, and they said, well, it uses an x86 processor, but the entire rest of it is nothing like a PC. The entire I.O. infrastructure, all of the chipsets, everything you're used to, forget it. It doesn't use the same kind of BIOS, doesn't use the same interrupts at all. So this leads us to Mike's question, which is, what is this A20 line? And I talked about it a little earlier. When the 8086 was a 16-bit processor, it had 20 address lines, A0 through A19. When they went to the 286, they extended the memory, but for backwards compatibility reasons, the machine boots up with the A20 line disabled, turned off. The way they do that is by routing it through the keyboard controller chip, because there just happened to be an extra line pin that they weren't using and a register that they could use to gate this thing. So enabling the A20 is something that every protected mode operating system has to do on a PC before it can actually physically use any of the additional memory on the system. And as for your question of what that piece of code would do, yes, it would sit there looping, continually trying, if I read that piece of assembly right, continually trying to write this magic value out through this I.O. port to which the keyboard controller chip is wired up to tell it, change this register to enable the A20 line. And it would keep doing this forever in a fast loop until it finally died. So where are you going here?
I was pulling up the new source code, so I was trying to pull up the file that you were talking about.
Okay.
Sounded interesting enough, and you sounded intrigued by it. So what was the file? Was it the...
It would be under, I think a boot, a init. Where are you? PWD. Oh, you're under Arch x86, okay. And what we're looking for is setup.s. There's header.
.ld. It's the closest thing I found.
this is a linker script that we were talking about.
Setup too big.
But
Well, makefile 32 should tell us where to look.
Rep minus R.
I'm a little too fast for me there.
there is no setup.
Well, how about in the IA32 subdirectory?
And
You also might search the directory tree on the words protected mode, because we know that the main thing that whatever this file is that we're talking about has to do is shift it into protected mode. Might also search on GDT.
The setup.s is under the M32R, and then it's M32R/boot, and then it's setup.s, at least on this 2.6.23 kernel source.
I'm sorry, could you?
Sorry, I apologize. Could you repeat that? Yes. If you look under the architecture /M32R/boot, there's a setup.s file in that directory, but that's the
That's a different processor.
I understand that, but that's the only setup.s I found in that kernel.
Okay.
Well, yeah, but what we're saying is the functionality may have been shifted into a different file name.
All right.
So from what I know about x86 architecture, I would search on strings like GDT and protected mode, because I know that functionally it has to shift the machine into protected mode by doing something with the GDT. So maybe the comments will help us find it. Well, since there's a whole lot of references to a GDT structure,
That's probably it.
by golly,
Oh my God,
it's the same source code. Okay, so let's go down to around line 800 or so.
What file were you in?
It's setup_32. Was that a lowercase s or an uppercase s? No, .c. Oh!
Oh, you didn't know that they converted a lot of the crap into C, did you?
What directory are you in?
I don't have the mic, so.
All right, I'll repeat it. It's
I have it right here.
Arch x86 kernel. That's from the top level.
I believe that there was an effort to convert a lot of this stuff into actual C code as well, so I think that there's much less assembly than there used to be. So.
And that's probably been true for the entire time that they've been doing the x86-64. That they found ways to generate a lot of that in C anyway.
I think that there were two separate efforts. I think that a lot of that cleanup is what drove this, but I don't know if it was like the same effort or if it was two separate things. So.
All right.
I have a question. On the kernel source I'm looking at, underneath the architecture directory, it's a I386. There's no x86. So I was wondering why some kernel sources have different labels.
Okay, so what I said is that they started, the question was why is it like IA32 here instead of I386, or why it's x86 under here and I386 there. The answer to that is the kernel developers move things around at various times, and specifically the merging of I386 and x86-64 into one architecture with two sub-architectures was primarily initiated. I mean, it's been out of the main tree for a while, but it was primarily started, the integration of that into the mainstream kernel started with 2.6.24. And you're looking at 2.6.23.
All right. Okay.
So, and this issue, how many people here have ever applied unofficial third-party kernel patches to your kernels? Not many people. I see Graham. That's about it. And Heather and Warren. Okay, a few people.
Other than ones that you wrote yourself.
How many people here have ever written your own kernel patches?
First part.
Okay, one. All right. So when you're grabbing these third-party patches and trying to apply them to a newer kernel, or if you try and apply 2 of them to the same kernel, sometimes they have collisions, but every once in a while you grab a patch that was written for 2.4.16 or 18 and try and apply it to a 2.4.21 with, it's a Red Hat kernel, which means it's been patched 900 ways from Sunday, right? And what you'll find is every once in a while they have moved entire directory trees of files around, right? Those files just disappeared right out from under you. And what you end up having to do to successfully apply the patch is go manually search for a chunk of code that looks like where the file used to be, find out where they moved it to. And sometimes what they've done is they've taken one file and broken it up into several different places, or they've taken a chunk of recurring code in several different places, abstracted it out, put it in a define somewhere, or in a common little library, and have all of the others calling it. So you're going to see they're constantly doing this sort of thing. You know, it's what makes it interesting. Yes? Okay, so I want to go back to init main.c.
Jim question.
Yes.
So if the A20 line is routed through the keyboard controller, then I'm a little confused on how this thing works in headless systems, which do not necessarily have a keyboard, mouse, or monitor.
Ah, the keyboard controller I'm talking about is in the chipset on the actual machine, on the motherboard, not actually out through the keyboard port. Okay. There's a different keyboard controller chip. Your common PC keyboard actually has a small processor built into it. I'm trying to remember, I think it's the 8042. There's one of them that's like an ancient history. There's like an 8040 something or another that was on the original motherboard, and that functionality has long been, merged into other parts of the chipset. Like North Bridge and South Bridge. I think it's somewhere in the South Bridge, right? So it doesn't actually have a separate processor on there anymore. But the old ones, maybe it was the 8059 was the one that was on the motherboard. That's the one that received the signals, and then the 8042 was a programmable chip inside the keyboard. And when you actually press a key, this is the old int16 stuff back in real mode. When you press a key, it actually sends what's called a make-break code. So it sends a code saying, I'm a key, I've been pressed, and here's my number. And when you release it, it says, I'm a key that's been released, and here's my number. And then when they went from like the smaller keyboards and did the extended keyboards, then all of those extra keys they added, things like the F11 and F12 when they started with 10 function keys, those actually say, I'm a key, I'm an extended key, here's my number. So if you actually watch at a very low level, you actually see like 6 codes. Every time you press one of those extended keys, which is like all the cursor control keys were added after the original. So you're seeing these streams of codes, and one of the problems back when I worked for Quarterdeck supporting QAMM was periodically you'd get a PC where the interrupts were a little too slow, and one of the most common complaints we would get is people saying, yeah, I'm typing along and suddenly it's just beeping at me. Okay, I need you to just hold down your Shift, Control, and Alt keys, hold them for a second, count, that's good, now let them all go. Everything's done. And then we would go in and we would put in a special flag to QAMM called U42, which says, this is a machine with an unusual 8042 controller chip in it, and so they would do something that was less timing sensitive to get rid of that problem. That's how absurd this stuff is. Anyway, I hope that answers the question. Yes?
So to make what Jim said generic, there's a couple of things. You have to remember that an operating system at its top level is about user interfaces, and that's a very standard part. And at the lowest levels, it's about connecting to hardware, and that's a very hardware-centric part. And unfortunately, you end up becoming a master of hardware trivia in order to understand the lowest levels of the operating system. Now, in this particular case, because Jim has a lot of experience, he has an enormous amount of trivia he can feed you. But you should remember that over time, they've been trying to take some of the agony out of making a PC. The PC was originally designed to be defective. It was designed not to compete with other parts of IBM's product line. And so moving to things like USB was in fact an attempt to sort of like make PCs a little less defective. So some of the stuff that he's talking about is a legacy from the original PC. If you go to USB kinds of control, keyboards and stuff, you'll find that it's not quite as arcane. So if you go to your, normally to your system, there's a folder, they try to make Linux look like Windows. And one of those little folders is going to be something that tells you about your memory map and your IO map, right? So it turns out that, as you click on those things and you see the device configuration table, you can actually figure out where Linux found things. And on old systems, you can find the old keyboard controller. On new systems, you find the USB controller and stuff like that.
Although, for a competing point of view, or an alternative point of view, USB could be considered by some to have a massive case of, shall we say, second system effect.
Yes. So,
but anyway, we're not going to turn it into a bait. I just wanted to get that little dig in there.
Second system effect?
Okay, for those who aren't familiar with the term, it is normal in the computing industry to come up with something that's kind of ad hoc and works. And then after a while, you need to extend it a little bit, so you kludge it, and then you come up with another kludge on top of the kludge. And at some point, you have this stovepipe. So then a committee gets together, usually a big consortium, and everybody decides this time we're going to do it right. We're going to make this thing so extensible that nobody will ever have to kludge it again. That's called second systems effect. There are lots and lots of examples.
They did like the second system effect.
So what are you doing?
Already had the second system effect undoing.
So I'm not disagreeing. There's an expression which says a camel is a horse designed by committee. And so what usually happens is that the most obvious problems in the old iteration get solved, but they fail to anticipate the future, so they lead you into another stumbling path where it's better than it was, but it still kind of sucks.
Amazing. Okay. Do we want to take a short break? I know we got a late start, so I'm willing to keep running. People are... Okay. So anyway, last week we talked about various places where you can start reading the kernel source code from the perspective of, I'm a CPU and I want to dive in just like the CPU did it. And we talked about what are the difficulties inherent in that. We also said, well, let's try and think of a higher level place where we can go. So let's jump on down to where it starts init.
All right, so can init set up here? Or?
Where it's execing init.
I would like to emphasize that we are jumping over a huge amount of material at this point. So we're jumping.
But that's actually a reason why I'm getting to this.
I'm not disagreeing. I'm just letting you know that we're taking a big jump. So if it has that flash forward, flash back feel, you're not crazy. Vertigo may be experienced in the audience.
So you may remember that at the end of head.s, what does head.s do? Does anybody remember?
Hey,
this is a family-oriented video. I am not repeating that. Oh. All right. So does anybody remember the function of head.s? What's the main thing it's doing?
Do I have to?
Yes.
He said that the bootloader jumps into this file.
Well, but I was wrong. It actually jumps into setup.s, and setup jumps into this after it's set the machine into protected mode. What directory is head.s actually in? Because there's a clue there. It's in the compressed directory. Because it's the little header of code that decompresses the compressed image of the kernel into memory. which means that you will not find it on most other architectures. Most architectures, they don't bother compressing the kernel because most architectures don't have this weird protected mode, real mode.
Actually, there's head.s and a whole bunch of alpha.boot, alpha kernel, rboot compressed.
How many of them are in compressed subdirectories?
Chris boot compressed. Okay.
Right.
Okay.
A few of them.
Correct.
And it may be, especially on the processors that are used more in embedded systems, you might find it on those, not because it's necessitated by the hardware architecture, but just because it's convenient. If you're on a 68K or a Chris, I know is a processor, it's almost exclusively used for embedded systems. So, in any event.
32-bit startup code.
So, at the end of head.s, it says that it's jumping somewhere. And I don't know where it's jumping to. I don't remember, and I didn't spend very long looking for it. But what we could do is stop Warren from flipping the screen around so much because I'm getting dizzy. Here, I'm going to take over. It's that flashing behind me. So one of the things I had said that we could do is here where if we boot it up in normal mode, it's doing this exec /sbin init, then it tries etc init, a few other things. We can track backwards from here and read the code and figure out what it did before then. Now remember, one of the things I said, when you're trying to read the kernel source code, one of the things you should do before you try and read it is think to yourself, what must have happened before we got this far? Like, when I was thinking about GDTs, I was thinking, even before I read that thing, I was thinking, wait a second, you need a GDT entry for every one of the CPUs, don't you? And then later, when I found the comment in there, I was like, oh, okay. So we talked a little bit about opening dev console before. You get all these weird comments in here. This is a non-init function. Force it to be no inline. So here's a little function that they created just for doing this. And before here, somewhere in here, we see the initial RAM disk stuff. Now, anybody know what an initial RAM disk looks like on 2.6? He does. How many people here have ever torn apart your initial RAM disks? Opened one up because you had to modify it? Okay. How many people here have any idea what an initial RAM disk is? Getting a little more response. Why don't I explain it? Yes?
Live CD. Mention that too. Go ahead.
Live CD. Yes. Okay. So, what's the kernel do? The bootloader loads the kernel and the initial RAM disk into memory. And actually, if we read very early parts of setup.s, there's another comment in there that's a little structure that says, this tells us what type of bootloader is calling us. And read this other file for the magic numbers set by Lilo and Grub and SysLinux to tell you who's booting you. But when it loads both of these files into memory, both of which are compressed, then it jumps into the kernel source, and there are different ways it can tell the kernel source where that other file is, which is described in there. It assumes it's going to be at a certain place, but then apparently there's something for different bootloaders to be able to load it in different places. The point is, you've now got this extra file in memory. In the 2.4 and earlier kernels, this was actually just a file system image. Any type of file system that you had built into your kernel could be used as your init RAM disk. So what the kernel would do is set up an initial RAM disk, just like you could create one yourself, and then it would decompress this file into it and temporarily mount it as the root file system. Then it would look for a file named linuxrc, an executable. This could be any type of executable, even a script, just so long as whatever script interpreter it needed, whatever shell, was also inside the initial RAM disk. And it has a little search path and everything that it knows how to find, and it has its own little linkages and everything, so that it can actually run a user-defined script before it's even found anything like a hard disk. Does anybody have any idea why you might need to do this? Of course you do. That was probably the reason you were ripping apart your initRD.
You might not have a file system or a disk.
Well, you might not have a disk. That's one good reason. You might be setting up a live CD.
Well, it's not trivial to read off of a hard disk.
Because you might have some bizarre controller where linking the actual controller driver directly into the kernel is difficult. You might be trying to be the Red Hat installer, and you might not have any idea what kind of controller it is. So you might have to do all kinds of hoops and weird stuff to detect or ask the user, what kind of controller should I look for? Well, what I/O port should I look on? We're talking weird SCSI controllers. We're talking RAID, hardware RAID controllers. And yet another reason is you might be booting off of a network. So what this allows is for the kernel to actually run a piece of code that was loaded into memory for it even before it has access to normal networking and to anything as complicated as a real disk drive. So that's what the initial RAM disk is. The older ones, like I said, was actually, usually it was a Minix file system or an ext2.
That's what everyone seemed to like.
Which one?
CramFS.
Or SquashFS or CramFS, which were a couple of specialized little file systems that were designed for nothing else. They were designed as read-only compressible file systems with no other purpose in the world. So there were actually at least two of those. So in the newer one, in 2.6, they redid that. Instead of having an actual, okay, with the old ones, you could actually take a Minix file system off of a floppy or use a loopback, right? And you just use a DD and create an empty file of a certain length. You don't want to just try and use normal makefs because it might create what's called a sparse file. And when you then tried to compress that or things, it would get very badly mangled. You would not want to do that. So you use DD if equals /dev0 of equals some output file and a size equals how big you want it to be, typically 1 meg or a couple of meg. I've used them even up to 8 or 16 meg in the past. All right, so they can actually get fairly large. Now on an x86 PC, I wouldn't go much above, say, 60 meg. I haven't done it any time recently. I remember that there used to be limits to it. But anyway, you take that, and then you do makefs-f to say force it, even though it doesn't look like a block device, pretend it's a block device, make a file system on it. You then mount it, mount-o loop. Is this review for a lot of people, or people have never heard this? Maybe I should actually show an example on screen. Of course, I have to be root to do that. You want to show an example on the screen behind me? My erstwhile assistant. So the whole purpose is you can create this, then the Linux kernel can use it. In 2.6, they changed things around a little bit. They no longer just use a plain old vanilla file system. They do is they make their initial RAM disk, and then they decompress a compressed CPIO file into it. So under the hood, this is referred to as initramfs. You read the kernel sources, you won't find, shouldn't find references to initrd.c anymore. It should come up as initramfs. However, if you install RHEL5 or CentOS 5, which uses a 2.6 kernel, or even CentOS 4, you're going to find that the utility for making one of these is still called make initrd. You're going to find a lot of the websites, a lot of the how-tos and things like that will continue to refer to it as simply an initial RAM disk or an initRD. The file names will still usually be initRD. Just understand that in the underlying source code, there are two important differences. One, if you're trying to read this and understand it, you're looking for initramfs. And two, it's no longer a simple file system image that you decompress and mount directly. It's a CPIO file. And in fact, if you're going to make the CPIO file, you can't just use GNU CPIO with its default output. The default GNU output format is wrong. The kernel uses the simplest possible one that has CRC checking. So, and I don't remember the exact one. Every time I have to fight with one of these bloody files, I have to use the file command to go, what kind is it? And then read the CPIO man page and go, was that it? And make one, and then do the file command again and make sure that the two matched up. And still sometimes I manage to get it wrong.
Can't you just Google? I mean, it's a commonly asked question.
Or I can Google it, or I can look it up in the make initRD, which is actually just a shell script. Yes, there are a few different ways to do it. And like I said, I deal with them rarely enough that every time I just have to go discover it all over again.
So, Jim, why don't you tell our lucky contestants why this is a good idea? What's the benefit of doing all of this?
Good question. So, I'm not really sure, to be honest. I do know that in the kernel mailing list, which, by the way, I have not regularly kept up on the kernel mailing list for several years, but some of the discussions were it could save some space because they don't actually have to carry around the same, especially the empty bitnode and inode structures that they used to. And the other thing that they've talked about, and I'm not sure if this is true, but somewhere in the near future they were talking about setting it up so that you basically have no choice. You must have an initramfs. So the old initial RAM disk, if you didn't have one, the system would go through its normal cycle. So it does a bunch of hardware auto detection. Well, okay, we talked about how it shifts into protected mode. After protected mode and before the point that we're talking about on the screen, there's all the hardware detection, and then somewhere, somehow, it tries to find your root file system, mount it up. When it mounts that up, then we see this piece of code here where it's going to open up your initial console and search for your init and try and run it. So this whole thing about finding your hard disk, basically, if you have no initial RAM disk, no initramfs, then it's going to look at its kernel command line and parse that. And if you don't have one of those, then compiled into it, there's a little major and minor number. And it's going to try and open up that major device and look for that partition, which is encoded in the minor number, and then just try and boot off, mount that up as root and use it for booting. How many people here remember the root flags command? We talked about that last week. Pretty obscure. All that did was it patched those little major and minor numbers at a static location in the kernel. Very, very simple. So I do remember that they were talking about actually doing away with some of that processing internal to the kernel and moving it into user space, and in so doing, absolutely requiring that you have an initial RAM disk. You have no choice about it, because as the kernel has gotten a lot more complex, could you bring up another window for a second and could you use an X term with the right settings as mine? Because I'm not sure people can read that.
Yeah, it's hard to read.
Here, let me bring up a... Well, that you can read, but...
So what are we trying to do?
Okay, in this case, I want a PS listing, pipe through less. PSFAX. We don't want just your processes. Okay. I don't have a laser pointer, but you can just point. No. Okay, thank you. So you see all of those thingies in square brackets? We talked a little bit about those last week. Those are all kernel threads. So these are little things that the kernel has started up for us that are fulfilling various different functions. Some of them are fairly complex, and one of the arguments in the kernel list is some of these things should be moved into user space. Now we talked last week about how in some cases what they do, for instance, okay, the classic Unix kernel only ever starts init. Never starts any other process out in user space at all, ever. Linux, and in fact I think a number of other modern operating systems, they actually break that rule a little bit for two purposes. Does anybody remember what the two reasons are? They're kind of two sides of the same coin. Come on, I know you know one of them.
UDEV will fork your little controllers.
Okay, so UDEV is a special case, but basically the KMod, kernel module loader, is one thing that spawns off an actual process, mod probe by default, something you can set through sysctl, but it spawns off a mod probe to try and satisfy device driver requests. So a user space process tries to access some kind of device, some kind of network protocol, some type of executable format besides ELF, like an old a.out file if you had one of those laying around. Any of those cases, the original process will be suspended, KMod will be activated with a little, basically a command line, telling it what type of device to try and load. It spawns off a user space process, which just runs a perfectly normal mod probe command out in user space, reads your etc modules.conf file to alias it and unalias it and do anything else and run all kinds of startup, pre-init and post-init scripts and all the other funny things you can do with modules.conf. So what was the other example?
AutoMounter?
No. Although it's an interesting example, I've asked this question before of exactly where AutoMounter hooks into user space, from the kernel into user space. It's a good example. What's another one though? No. So dmessage actually is very, very simple. Print Ks go into a ring buffer. Well, depending on what number, what severity level is prepended to them, they either go in or they get filtered out. But assuming that you have your threshold set low enough, a print K goes into the ring buffer, and the dmessage just reads through /proc kmessage. It just starts at the current tail of it and wraps around. Meanwhile, there's another daemon on your system called klog daemon, and all it does is basically, effectively, tail-f, although this doesn't actually work. If you ever try it, it won't work. But it effectively does the equivalent of tail-f of /proc kmessage. And every new message that comes into the kernel ring buffer, it relays to the syslog daemon. So if you've ever looked at the package, if you do rpm-qf on /proc syslog-conf, you see the package name is sysklogd. That wasn't somebody just had a typo or a hiccup at the keyboard. That actually is the combination of syslog daemon and klog daemon in one package. And klogd is, as far as I know, unique to Linux. I've never seen klog on any other form of Unix. So anyway, the other one I was talking about was hotplug. Right? So you slap a new card into the side of your machine, and it's not, from the kernel's perspective, this is an entirely different event than when a user process has tried to access some non-present device. Right? Now some device has come onto the system, and the kernel wants some way to spawn off a user process to figure out what to do with the bloody thing. Right? If it's a device like a USB hard drive or something, it wants to know, what should I call it, where should I mount it? If it's one of these little, Verizon EVDO cards, it wants to say, okay, what kind of user, PPP chat script do you want to initialize this device and set up the networking for it? And I'm sure, even for things like, USB keyboards can activate your hotplug-d. Although traditionally, and this has changed a lot in recent kernels, traditionally you actually had a separate USB hotplug daemon and a whole little infrastructure for dealing with that was all under /proc bus USB. So that sort of stuff gets complicated. Brain dead. Okay. Any questions? Anybody need to take a break? Okay. So, where are we going to go from here? I'm going to track backwards a little bit further. So this to me is kind of interesting. We see that just before it defines the run init process, it's spawning off. So we've got these functions named things like spawn ksoft_irqd and whatever the heck that thingy is. I don't think this one even has one of those square bracket thingies around it. Might not show up in a PS listing, I'm not sure. So why don't we go to ksoft_irqd? Because I'm curious, what does it actually do? I'm guessing it has something to do with interrupt request management. Maybe assigns interrupt requests to processors or something? Okay, so that's where it's referenced, but I want to see where it's defined. Not much comments in here. Let's see. So can anybody tell me what that's doing?
Which one?
This ksoft_irqd. It looks like it's only starting one process, not one per processor.
Well,
This looks like it's actually turning on the register.
Well, okay, so the first line, the first line is a CPU structure.
So it's getting the mobile CPU structure and then executing a few things on it.
Int error equals CPU callback, CPU up prepare on the CPU.
The address of the callback, the flag, the number of the CPU it's called for.
So this must be a structure that holds different functions for the CPU, so it's preparing the...
well, so when you power up and you power up SMP, one processor wins arbitration and you power up uniprocessor, right?
Right. At that point, you only have one processor running.
Right, and all the other ones are in a special state, okay? And it takes a special invocations
Can
sequence.
you do the mic?
Oh. I'm sorry. So when you boot multiprocessor, one of the processors wins arbitration on the, basically the interrupt bus. And all the other processors go into a special state where they're almost uninterruptible. They act almost like they're electrically dead weight on the system. They appear as if did not exist, and there's only one specific wake-up sequence that will actually pull them out of that state. So when you say CPU up, prepare, and it also has bug on, error equals notify bad, there are specific things in the Intel MP protocol which are about saying, hey, I didn't make it through post successfully, you should leave me alone, okay? So since he didn't really comment all this stuff, I just happened to project into that space what those names mean. We would probably have to follow it through to make sure I'm correct, but that's what that really looks like.
Actually, I want to see, go back one, because I'd like to see a CPU up prepare.
Well, this is more than likely a constant to identify, so yeah, it's just a macro. So
Well, but let's see it.
yeah, maybe it'll do something useful.
3.
So
Yeah.
I think that we have to look at the
Yeah.
callback to see what it's actually doing. So in the prepare, okay.
Okay, so it's one of the actions it can do in a CPU callback.
So one of the things to keep in mind is that in the Intel architecture, we have a programmable interrupt controller, and it turns out that you can basically reallocate interrupts. So you can move them around, and so when they say soft IRQ, they mean that this is sort of like an initial configuration, and we're going to change this later.
remember, this is a fairly late stage after all your devices are initialized.
I think that's scheduling a software interrupt to enable the one processor, I guess. I'm not sure.
I actually don't think so, but let's do this, if I could.
Sure.
Some of this is probably in hardware, so that there's probably a standard. So is it commingling of hardware and software? So some things might not be apparent from reading the software.
Well, what I'm going to do, because I'm not an expert on this stuff, is I'm going to refer to the universal expert on practically everything. Sure glad none of my friends who work at Yahoo are here right now. So, let's see. Unfortunately, there's actually, that's funny. Did I misspell it? No. Or I must have.
Take the K off. Just do soft hierarchy.
Kernel analysis how to, Linux peculiarities. Maybe that'll explain it. Okay, so oddly enough, this segues into what John was commenting on earlier, and I'll just mention it briefly so we don't have to read this stuff on the screen. Traditional Linux kernels, everybody has heard of virtual memory? How would you define virtual memory if you could do it in like one sentence?
Memory on disk.
Huh?
It said memory on disk.
Well, traditionally, people refer to it perhaps as memory on disk or paging, or simply the concept that the user space view of memory, that there's this contiguous region of address space, and you just get to use however much of it you asked for and got. And under the hood, the kernel gets to see memory in a whole different way. It gets to take some pieces of that and map them into multiple separate processes, so that each process thinks that he is the sole owner of this page of memory, but in fact, it's being shared among a whole bunch of them. And if it's in your readable read-write address space, then when you write to it, the kernel detects that, puts you to sleep for a little bit, makes a copy of it just for you, and then wakes you up when you have your copy. That's a concept called copy on write. All modern operating systems do this to some extent because it's a huge win. Now, this also allows the system to do things like take a bunch of your memory that's allocated to you, but you haven't used recently. And what the kernel can do is say, well, since he's not using that, I'll just kind of shuffle it off to disk and throw it away, free up this space for somebody else, and then when you try and access that again, he puts you to sleep, possibly for a very, very long time, while he swaps that stuff back in and then lets you access it again. So that's why we tend to think of virtualization as memory on disk. Now, we almost throughout Linux, we refer to that as swapping, but technically very old versions of Unix actually had two different concepts, paging and swapping. Swapping was where you took an entire address, an entire user space process, took the whole thing and tossed it out to disk. Some kind of a batch processing mentality. I am too busy and things are taking up too much memory right now. I'm going to put that whole thing to sleep for a long time. Linux doesn't do that. Linux at various different times in the past has had some patches that allowed it to do that, but actually that issue has been debated on the kernel list on a few occasions. I remember one of them being somewhat of a flame fest about 10 years ago. So I'm not sure that the Linux mainstream kernel has ever actually had swapping in the mainstream kernel. As far as I know, swapping in Linux has, in terms of the mainstream kernel, has always been a misnomer. It's actually always been paging, and some people have implemented third-party, unofficial patches to implement it. Now, I could be wrong on that, and if you find an example, a counterexample, then prove me wrong.
Should I add to the discussion, or should I just let you go on?
I don't know. What do you want to add? Go ahead.
So everything Jim said was true. He might have left out one little thing, and that is it used to be that computers did not have enough memory. So it used to be that when you loaded a program, you had to load it entirely in order for it to fit. So the first thing they did is they said, well, if I don't have enough memory, I'll just throw out the inactive process. And there was an advantage to that because disks have an enormous amount of bandwidth but very poor latency. And they say, I'm just going to write, if I have to touch the disk at all, I might as well throw them all out. But then, of course, what people found out is they said, well, that's not such a really good idea after all, because it turns out that this throwing everything out and pulling everything back in tends to take a long time. So what they did is they looked and they said, in every program, you're normally only executing a small portion of the code. You're normally only referencing a small portion of the data. So if instead of throwing everything out, all I do is I throw out the inactive sessions, then it turns out I can fit more stuff inside memory, more useful stuff, and I can have more concurrent activity going on, which is what an operating system is all about.
Okay. So could you go back up to where it's talking about the Ksoft IRQ stuff? We notice it's the last thing it's doing before dealing with the initial RAM disk. Thank you.
Oh, sorry.
Yeah.
It looks like what it's doing is just queuing interrupts and then using the software interrupt to process them all at once or something.
Well, okay, so I do know that there's this concept called processor affinity. So if I have an interrupt request come in, remember an interrupt request is a hardware event that needs to be bound to a particular software driver or handler. And John mentioned earlier, should we talk about bottom half and top half? And we did mention it very briefly last week that in most operating systems, device drivers are divided into, or interrupt handlers, interrupt servicing routines, divided into two parts. One is the absolute barest minimum I can get away with to save enough state that I can deal with it later. So for something like a serial line, then the absolute minimum I can do is grab whatever bytes are in the hardware buffer. If it's, let's say it's a 16550, it has a, which is a very common universal asynchronous receiver transmitter semiconductor, a UART, it has a little 16-byte buffer on it. So when it signals an IRQ to me, it can continue to buffer up a few more characters before I get to service it. When I get to it, what I'm going to do is grab all of the characters that are in its little buffer that I can and shove them someplace. Maybe I have a little 16 or 32-byte chunk of memory in my device driver that I always have that I just use as a little ring buffer. So I just grab it, shove it onto my ring buffer, clear the little bit that says it's okay to start receiving again, and then I move on. And meanwhile, I've scheduled for my top half, that was my bottom half handler, the part that's closer to the hardware. So my top half has now got a little flag in it that says, oh, next time you happen to have a little time slice, go in here, copy this out of there, update this little flag that tells me where my new tail is on my ring buffer, and send it off to wherever it's supposed to go. All this complicated stuff about figuring out what user space processes or C-level buffers, C programming type buffers, are actually associated, connected to this serial device in some way. That's all more complicated stuff that you don't want the bottom half to handle. Anyway, this concept of affinity is where if one of the processors handled the serial interrupt the last time one came in, then I would sure love to give him the next interrupt that comes in from that device, because in his first level cache and in his second level cache, he's already got the code that handled it the last time. probably. He's far more likely than any other CPU on the system. So wherever possible, you want to try and route the IRQs to whatever processor handled them recently. And the same is true when you're doing process scheduling. Whoever most recently ran a particular process, next time he comes up in the run queue, you'd like to give it back to the same processor unless that processor is overloaded. And that's where a lot of your really complicated scheduling stuff comes in, where they're trying to track this stuff and figure out when they need to redistribute processes to other processors or interrupt service routines to other processors. I get to use some of the same logic because a lot of these things they've spawned off into kernel tasks that look like, they have their own process IDs and are scheduled the same way as user space processes, even though they don't actually have a user space address space. Remember the one thing I said that I can pretty much guarantee you is different about all those things with the square brackets around them, all the kernel tasks and the user space ones? What was the one thing I said that you could pretty much guarantee is different between them? Right, whether or not they actually have any user space memory associated with them, which is in proc maps.
You want to see that?
Huh? Sure. No, it's in a process. So go to 1. Process 1, is a normal user space process. So that is user space mappings. Now find one of these, just do a PS FAX pipe head. And let's grab, number 2. There isn't one. Actually do an ls of /proc/2. Just so they can see that it's, so it exists, but it's a completely empty file. So every normal process under there, every user space process, has to have a non-empty maps file, or maps virtual file. Yes?
Warren, what kernel are you using?
uname-r.
He just asked what kernel am I using. So.
Yes.
Why, as we read the source code, we want to know?
Okay, 2.6.22. I think that with the occasional exception of something like a fairly major transition in, .24, most of the discussion here I would expect is not going to be that sensitive. We're going to talk usually in terms of 2.6 versus 2.4 or going back to, 2.0 or, remember that last week I pulled up, just for comparison's sake, looking at the old 1.0.9 kernel, right? And it would be, I think, very useful for us while we're reading this on our, and I've been doing it myself, to go back and look at different kernel versions. Like that the first version of Linux that supported SMP, I think was either 2.0 or 2.2. So go back to its main.c and look backwards from where it starts execs init and see what kinds of things it was trying to do to start up these things. I know that was long before they had all these funny, k-migrate and stuff like that.
No, my point was that things change in /proc, and they change a lot more frequently than the major other structures of the kernel. So to look at 22 source code while trying to find out. So things change in proc with a little more rapidity than they might elsewhere. The way that the features reflect themselves in the proc file system, it may not be as useful to read 24 source code and then look in the /proc file system on a machine that's running a 22 kernel.
Well,
there might be a little difference.
All right. So keep in mind that as soon as the kernel developers put something in the mainline kernel under /proc, they've promised to keep it there for a while. Now, they may add some additional stuff. For instance, they might add more stuff at the bottom or more stuff at the ends of each line so that well-written code that's reading it will ignore all of the excess stuff that it doesn't know what to deal with but it becomes a contract to user space. So anything they put in there, they have to keep there for years to come. The last time I had a kernel that severely broke user space utilities because of changes to proc was somewhere between 1.0.9 and like 1.1. Something or another on the march to 1.2, where I installed a new kernel and did a ps command and it core dumped. And all of the proc ps commands were all core dumping all over the place. It was the one time in my entire career as a sysadmin that I was very glad that I had already developed the habit of having a root and an alternative root, because I needed to be able to test this new kernel on this server, but I needed to be able to go back and forth between them. So what I did was I installed the new kernel and the new proc ps on my alternative root file system and set up my two boot entries so that I was booting either the old kernel with the old root file system or the new kernel with the new root, and ne'er the twain shall meet. Because the only other choice would have been somewhere very early to do some weird link renaming or copying or stuff that, and when that stuff was that broken that the ps command didn't work, I wasn't about to be trying to rename files during the RC scripts. So, in any event, just my thoughts on that. Let me go back over here. Now, certainly I would love to read a lot more about what SoftIRQ is doing, because this is kind of written, I mean, you know, I see this thing here, _CPU 0, and I'm thinking to myself, that sounds like there should be one of those for every CPU. Well, let me see it again here. I could have just missed it because I was too busy talking. Okay, oh, here we go. Well, there's oh, you only have actually one processor on here, don't you?
Yes.
Okay, at work, almost every machine I log into except for our laptops are all like these multi-processor behemoths. So
I have a hint for you. There's very few SMP laptops.
actually, these days, most of the new ones coming out are dual core or hyper-threaded.
Yes, but hyper-threaded don't behave the same.
Okay, so Heather says hyper-threaded doesn't behave the same, and actually, at one layer of abstraction, as far as Linux is concerned, a hyper-threaded processor, cat/proc CPU info, you're going to see two CPUs in there.
I will say it's got the same, but it don't act the same.
Doesn't matter. From the reading the kernel source code, the differences in the Linux kernel source code, a hyper-threaded processor is treated as an SMP system. That's by design. That's the way they design the hyper-threading features. Does everybody know the difference between hyper-threading and dual core? Okay. Dual core means I put most of two CPUs on the machine. So there are two processing units that just happen to be sharing one die and one L1 cache. But that's kind of expensive to get ramped up for your first production. So time to market considerations, what Intel did is they said, well, wait a second, instead of putting a whole extra CPU on the die, why don't we just put an extra set of registers? And then we'll set it up so that basically whenever we have an L1 cache miss, then we'll just save that set of registers, switch over to the other set, and see if maybe the cache is warm for that one. And by the time we get back, maybe the cache will be warm again. Now, when you're talking about running Windows, where there's very little locality of reference and there's all kinds of stuff that's very user-driven, the GUI is always going to be busy doing something, usually something that's not local, then whatever you're really trying to do can be using up one task on the CPU, one set of registers, and whatever your user interface is doing can be handled when it comes around, when you get a chance, because it's going to have this very spotty cache performance. So actually, hyperthreading is a great win for interactive use mixed with a little bit of, more hardcore what's going on under the kernel. when you get into things like, okay, the company I work for does electronic design automation software. Very expensive software, uses up tremendous amounts of memory, and it uses all the CPU you've got and then some. And because of the way they do license management, we actually, for years, where I work, disabled hyperthreading because it wasn't worth the extra seat in the license manager. The extra performance you got out of it wasn't worth it. Now, actually, FlexLM, which is one of the big license manager packages out there, I'm sure most of you know that, they actually modified their code so that they can detect, in newer versions of the kernel, if you do cat proc CPU info, I don't see it in here because, of course, this isn't hyper-threaded. There would be an entry over here that says siblings or number of siblings. All right, when you're a dual core or a hyper-threaded machine, then you can tell because the processor has siblings as opposed to each having its own separate processor ID. It has one of those as well. That's for backwards compatibility. But they just add this extra entry to give you a hint that it is either dual core or hyper-threaded. And then somewhere down in these flags, you're going to see some kind of a little flag. It might just be HT, but I don't remember.
It's HT, and it also shows up on certain machines that are not actually hyper-threaded.
One of the problems is that the flag can show up, but the vendor who integrated this processor onto their motherboard might have disabled it on the motherboard. Or it might be disabled somewhere in the BIOS, and you might not have a switch to re-enable it.
Well, I don't think that those are the only issues, because this thing was never... I think that they actually had...
Microphone?
Well, no, just let him finish, and I'll repeat what he said. Or we can hand him the microphone.
Yes.
All right.
I apologize.
So, yeah, Warren is talking about hyperthreading and how the HT flag in proc CPU info, to his experience, seems to be pretty unreliable.
And it's simply because I have a laptop at home that shows the HT flag, but it's not actually hyper-threaded. And this happened in very early P4 CPUs, and it's thought that either they put it in the CPU ID information for some reason before they actually released the CPUs, or possibly that these processors were not certified for hyper-threaded use. So it is possible to see it without it. I do want to make one other comment, though. We need to start wrapping up because it's 9:30. So.
Okay.
All right.
I was going to mention the last thing.
So I was going to mention something about soft IRQ. It's interesting that since the Linux community has gotten very large, you can sometimes see the effects of politics in the source code. So, yes. Well, so.
Shocked.
What?
I'm shocked. Go ahead.
So.
This one here was just the results of doing the following Google search. Linux, Ksoft IRQ, and it was one of the things down here.
It's the first one. You're feeling lucky.
Ah, yes, I'm feeling lucky. I am lucky. Yeah, you might also just search on kernel analysis how-to.
So normally, if you take an introductory computer architecture class, the notion of an IRQ is it's an interrupt, which means it says it's a signal to the processor which says go off and do something now, okay? But if you read the description, you'll say, well, these interrupts are, quote, deferred. And so in other operating systems are called deferred interrupt handling. And what's important about that is that in modern processors, which run at 1 to 3 gigahertz, they run so much faster than memory that, in fact, there's an enormous amount of time it takes to service a I/O interrupt. So what they do is they actually record the fact that interrupts happened, but and they process them in a batch. But the problem with that is that it hurts real-time response. And Linux serves a variety of communities, and by calling it a soft IRQ instead of a deferred IRQ or a deferred interrupt, the people who got shorted by this design decision aren't quite put on as notice as they might otherwise be.
So, Paul asks, is there any chance that we could do kernel boot parameters next week? And that actually poses a really complicated problem. We can try and find the first bit of code that the CPU would encounter that does any command line parsing. But how many people are aware that your /proc has this little entry called CMD line? How many people have ever used that? Okay, it preserves the arguments as passed to your kernel by your bootloader for eternity, basically, for the entire duration of a kernel session. One of the reasons that this is important is because there isn't one place. Okay, in a normal C program in user space, normally you have pretty much one function right up near the beginning that says, go parse my command line and set a bunch of options and be done with it. All done with that. You can throw that thing away now because we don't need it anymore. We know what we're going to do. That's not the way the kernel works. There are little parts of it that say, oh, mem equals. Well, before I do any initialization, I better check and see if there's a mem equals that says I'm supposed to use less than the actual auto-detected amount of memory. And root equals, well, maybe I'm going to use that. I know that on a Red Hat system, I say root equals /dev vg0 / something or another. That's actually using logical volume management, LVM. Obviously, the kernel isn't going to know what to do with that, right? So what would be the point of even parsing it? And there are certain things where you can pass kernel command line arguments for things that you don't even have modules for. And yet, when you load those modules, they go check /proc CMD line. They do their own parsing. So in other words, there's no single place in the kernel. I tried this once. I tried to find the place where it parses the command line. Right. Doesn't happen. There are different parts that check for different things scattered in different places of the kernel.
So I have this idea, Paul. Why don't you find the top 5 things
right.
that you think would be on your hit list for finding out about the command line parameters?
Well, let's see. We pretty much know where to find init equals. Root equals would be interesting. Mem equals would be interesting. And reserve equals. Anybody know what reserve equals does? I want to know if anybody in this room has ever had to use the reserve equals kernel command line parameter.
I got an idea. How about people who feel that they've got something that might be a good topic for one of our presentations, study things, gatherings for this study group kind of thing, put a list or the item on the Wikiversity page for this?
Yes.
Reserve equals reserve an IRQ for something?
No. It reserves a range of I/O ports to say, don't touch that. Leave these alone. It's essentially like mem equals. All right, there's also an exclude equals that says exclude a range of memory. Mem equals says don't use more than this amount of the system's memory, so cap it off at the top. And reserve equals says these particular I/O ports, there's something very bad there. If you touch them, it'll hang the system. Or even just, I don't want you to touch these I/O ports.
That comment that you made about RAM,
yeah.
It's interesting to note in the past you used to have to use that to actually detect all of your RAM. So.
Oh, yeah. Okay. Yeah.
So.
Warren makes an interesting point. Back on old broken bits of hardware, earlier versions of the kernel used a particular interrupt. I think it was the BIOS interrupt, that's a firmware interrupt 12, to say, how much memory have you got? Well, early versions of the kernel didn't know how some of the BIOS manufacturers had extended this BIOS functionality and had a different way of doing it. So it would lie to you and say, you have, I don't remember what it was, 32 meg of RAM. And it would lie to you because that was the maximum that was allowable in the old BIOS standard. But if you put some magic values in the AX register or something like that, and then you called it, then if you looked in a different place than where it normally told you, it would tell you the real answer. So before you had that, before the kernel knew how to auto-detect on these funny systems, you could just tell it, look, I actually have 64 meg of RAM. Don't ask, just go use it. And it would do it, because that's what the option was there for. The other purpose of it, and it's pretty much the only thing you'd use it for on any modern system, is your boss gave you a nice 2 gig system, but you're a software developer, and he tells you, you better make sure this runs in 256 meg of RAM or you're fired. Well, you could ask him for another machine, but he might not like that idea very much. Or you could just boot it up with mem equals 32 or 256 or whatever it is and lie to your machine. As far as the Linux kernel is concerned, that machine only has 256 meg of RAM and you're fine. So it's good for testing.
So everyone, give Jim a hand, please. And thank you for coming out to...
And edit the wiki.
And thank you for coming out to SVLUG. That is wikiversity.org.